Today we're diving into Bulletproofs, a really clever cryptographic breakthrough that's basically rewriting the rules for privacy on public networks like blockchains. So let's get right into it.
Okay, so it all boils down to this one huge question. How do you prove something you know is true without actually showing anyone your secret? Think about it. You want to prove you have enough money to buy something, but you absolutely do not want to flash your bank balance to the entire world. This is the exact puzzle that zero-knowledge proofs were invented to solve. And bulletproofs, well, they have a particularly slick answer.
But, to really get why bulletproofs are such a big deal, we first need to understand the scary problem they were built to fix. And it has a great name, the toxic waste problem.
So some of the earliest and honestly most efficient zero-knowledge proofs, like ZK SNARKs, had this one major catch. They needed what's called a trusted setup. This was basically a special ceremony where a group of people would get together to generate some public keys. And to do that, they used some secret random numbers. The entire security of the system then depended on every single one of them destroying those secret numbers afterwards.
And here's where it gets dangerous. If just one person in that ceremony decided to hang on to those secret numbers, the so-called toxic waste, they would have a secret master key. They could create fake proofs that would look totally legitimate. In a cryptocurrency, that's like having a secret backdoor to print money out of thin air. It completely breaks the system. You just had to trust that everyone did the right thing.
And this table really lays out the dilemma perfectly. On one side, you've got those ZK snarks. Yeah, they need that risky trusted setup, but wow, their proofs are tiny, like incredibly small. On the other extreme, you have ZK starks. They're transparent, meaning no trust needed, which is great, but the proofs are gigantic, often way too big and clunky for a lot of blockchains. And right there in the middle is the hero of our story, bulletproofs, transparent and trustless, with a proof size that's totally manageable. It's the sweet spot.
And that's exactly where bulletproofs come in. They showed up with a transparent solution that just throws the need for trust right out the window.
So what's the secret sauce? It really boils down to two huge things. First, as we said, no trusted setup. None. Its security is based on a really old, well-understood math problem. So you're not trusting people, you're trusting math. Second, and this is super clever, their proofs have what's called logarithmic size. All that means is that even if a transaction gets 100 times more complex, the size of the proof barely gets any bigger. It's just the perfect balance. The magic trick behind this amazing efficiency is something called the inner product argument. Now, stay with me here. It sounds complicated, but the idea is actually pretty intuitive. Imagine you have a giant detailed map. To make it smaller, you fold it in half, then in half again, and again. The protocol does something similar. It takes these long lists of numbers and step by step folds them down, combining them until you're left with just a couple of tiny values. It's a brilliant way to squash a ton of information into a tiny verifiable packet.
Okay, so now that we know how they work, let's talk about their most important job, keeping our financial transactions confidential. This is where bulletproofs really shine. Now, this might sound a little bit technical, right? Why is this one specific proof that a number is positive so critical? Well, in a private system where all the numbers are encrypted, this check is everything. It's the bedrock of economic security. How do you stop somebody from sending, say, negative $100? Because if they could do that, they would have just magically created $100 for themselves.
And there's your answer. You need what's called a range proof. It's a simple guarantee that an encrypted number is in a valid range, specifically that it's 0 or more. Without that check, the whole system falls apart. Anyone could just secretly print money and the entire currency would become worthless.
And here's another game changer, aggregation. Instead of creating a whole bunch of separate proofs for every part of a transaction, bulletproofs lets you bundle them all into a single compact proof. Just look at the difference here. For a transaction with 8 different outputs, the old way would be a hefty 20 kilobytes. With bulletproofs, it's less than 1 kilobyte. That's a 96% reduction in size. It's staggering. And if we zoom out to the big picture, it gets even more dramatic. Some researchers calculated that if you used bulletproofs for every single unspent transaction on the entire Bitcoin network, the data needed for these proofs would shrink from 160 gigabytes all the way down to just 17. That's an 89% drop. That is a massive efficiency gain that makes the whole network cheaper and faster for everybody.
And this kind of efficiency isn't just theoretical. It has huge real-world consequences. So let's take a look at how this technology has just kept evolving, getting smaller, faster, and stronger over time.
Monero, the privacy-focused crypto, is the perfect case study. Back in 2018, they upgraded their network to use Bulletproofs, and the results? They were revolutionary. Average transaction sizes dropped by a whopping 80%, and because fees are tied to size, they plunged by over 95%. This was an absolute game changer for making the network actually usable. But, the story doesn't end there. Not even close. The crypto space never stops innovating. The moment the original Bulletproofs paper came out, researchers were already figuring out how to make it even better. So the original 2017 protocol gave us a single range proof that was 674 bytes. That's already incredibly small, a huge leap forward. But then, just a few years later in 2021, we got Bulletproofs Plus. They found a more efficient way to structure the proof, and boom, they shaved off nearly 100 bytes, bringing the size down to 576. And then, just 1 year after that, Bulletproof Plus Plus hit the scene. This version used a totally new technique, and the results were amazing. The proof size plummeted to just 416 bytes. That is a nearly 40% size reduction from the original design in just 5 years. The pace of improvement is just wild. Of course, it's not all a perfect story. No technology is flawless, and it's absolutely critical that we understand the risks and the challenges that come with something this advanced. Case in point, a really serious vulnerability that researchers found in 2022 called frozen heart. Now, it is so important to get this next part right. This was not a flaw in the math of Bulletproofs itself. The protocol was sound. The problem was a subtle but critical mistake in how some projects actually wrote the code to implement it. So how did this attack actually work? It was pretty clever and kind of scary. The whole proof process involves creating this unique digital fingerprint, or hash, of all the transaction details. Well, some of the code out there forgot to include one of the public values in that fingerprint. This tiny oversight was enough to let an attacker take a perfectly valid proof for, say, $1, and then swap in a commitment for $1 billion, all while tricking the system into thinking the proof was still valid. And then, if we look even further down the road, there's the quantum threat. The security of Bulletproofs, and a lot of modern crypto, is built on a math problem that's basically impossible for today's computers to solve. But a powerful enough quantum computer could potentially break it. Now, this is a long-term risk, but it's a serious one, and researchers are already working hard on building the next generation of post-quantum cryptography to defend against it. So all of this leaves us with a pretty big question, doesn't it? Bulletproofs came along and solved that toxic waste problem, proving that we can have powerful privacy without being forced to trust some small, privileged group. As more and more of our lives go online, the need for this kind of verifiable, trustless privacy is only going to get bigger. The question really isn't if we can achieve it anymore, it's how we're going to choose to build it into the very fabric of our digital world.